Today we learn the last point of this topic, application of logic to switching circuit. A logical statement is either true or false, that is, its truth value is either T or F. A similar analogy is observed in electric device. For example, an electric switch is either on or off. Let's see switch definition. An electric switch is a two-state device used for turning a current on or off. If the current passes through an electric circuit, then circuit is closed, that is on, and if the current does not pass through it, then it is open, that is off. Remember, if current pass through circuit, then circuit is closed or circuit is on here, and if current does not pass through circuit, then circuit is open or off. Let's see, this is the diagram for closed switch and this is the diagram for open switch. In figure 1, this figure, switch is closed, that is on. This is the switch is on, hence the current flows. And in figure 2, this figure, the switch is off, that is open, hence current does not flow. This is the off circuit and this is on circuit. Consider a circuit containing an electric lamp controlled by a switch. This is L means lamp and this lamp is controlled by this switch. Switch is denoted by S. Now this switch is battery and this switch is S denoted here. When the switch is closed, the current flow in the circuit and hence the lamp glows, that is the lamp is on. This switch is closed, then current flow to the lamp and lamp is glow and lamp is on. Now when the switch is open, then current does not flow in the circuit and hence the lamp does not glow, that is lamp is off. When this switch is open, then current does not pass through the lamp here, then lamp does not glow or lamp is off. Let here this statement write down. This is P, switch is closed and L means the lamp is. Note here, we associate a closed switch with a true statement and an open switch with a false statement. When switch is closed, then we say true statement, and switch is open, then we say false statement. Hence in an electric circuit, if the switch is on, that is closed, then its truth value is T or 1. Remember, when circuit is on, then its truth value is T or 1 denoted, and when switch is off, that means open, then its truth value is write down F or 0. Switches in series. See here diagram. This switch, this circuit and this S1 and S2 switches here, S1 and S2, correction here, this is S2. This switch connected in series. This position is called in series. See here, if two switches are connected in series, then current will flow through the circuit only when both switches are closed. Remember, if both switches are closed, then current flow to this circuit. Let write down first P statement is the switch S1 is closed, and Q statement write down the switch S2 is closed, and L means lamp, the lamp glows. In this case, the lamp will glow if and only if both the switches yes and S2, remember here, and S2 are closed. That is, P and Q is equivalence L. If both switches are closed, then current pass through this circuit and lamp is glows. Here we write P and Q. This is P statement, this is Q statement, and write down AND. Table for this. This is P statement and this is Q statement. Here write its truth value. T means 1 and F means 0. We know that P and Q is T, F, 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 and write down in bracket 1, 0, 0. Next, switches in parallel. This diagram here, S1 and S2 are connected in parallel. This position is called parallel. If two switches are connected in parallel, the current will flow through the circuit even if any one of switch is closed. Let here, if one switch is closed, then current pass through this lamp. Not both, if any one, S1 or S2, if closed, then current passes through this lamp and lamp is glow or on. Write here statement. P, the switch S1 is closed. Q, the switch S2 is closed. L, the lamp glows. In this case, the lamp will glow if at least one of the switch is either S1 or S2. Remember here, or S2 is closed. That is, P or Q is equivalent L. Means both, at least one is closed, then lamp is glow. Since we write here or, P or Q, and we know that truth value, this is truth value, and write down in bracket T means 1 and F means 0. Input output switching table. This table is called input output switching table. Some definitions. First, equivalent switches. Here, two or more switches in a circuit which opens or closes simultaneously and are denoted by the same letter are called equivalent switches. Second, equivalent circuit. If the output of the two circuits is same for all possible combination or way, then these circuits are called equivalent circuit. Third, simpler. A circuit contains less number of switches, then it is called a simpler. Next, complementary switches. Any two switches in a circuit having opposite effect or states are called complementary switches. For example, if S1 and S2 are two switches such that when S1 is closed and S2 is open, vice versa, then switches S1 and S2 are called complementary switches and S2 is denoted by S1 dash. Here one of the switch is considered as P and other as negation P or P dash. Remember, this is complementary switches. Next, negation state. Consider switches S and S dash associated by their states such that if S is on, close, and S dash is off, that means open, and vice versa, then switch S dash is called negation of S. Here statement P, the switch is closed, and Q means the switch is not closed or open. Opposite of this is not closed or open. Input output switching table for this is P and this is negation P. If P is T, then negation is F, and if P is F, then negation P is T. That means 1.